which in turn permits further seawater to penetrate, perpetuating the process. The scale of such reactions is astonishing. The volume of water bound into rock in this way is believed to equal the volume of the oceans themselves. As the ocean floor spreads, these expanded, hydrated rocks ultimately plunge beneath a colliding plate, where they are superheated again in the mantle. Now they give up their water, releasing it into the bowels of the earth. This contamination with seawater drives the convective circulation deep in the mantle, forcing magma back up to the surface at the mid-ocean ridges and volcanoes. And so, the turbulent volcanism of our planet is largely driven by a continuous flux of seawater through the mantle. It's what keeps our world out of equilibrium. It is the turning of our globe. But the reaction of seawater with mantle-derived rocks does more than just drive the relentless volcanism of our planet. It also releases energy as heat, along with copious quantities of gases like hydrogen. In fact, the reaction transfigures everything dissolved in seawater as if it were a magic distorting mirror, reflecting back grotesquely swollen images in which all the reactants are loaded up with electrons. Technically, they're said to be reduced. The main gas emanating is hydrogen, simply because seawater is mostly water. But there are small amounts of various other gases, reminiscent of Stanley Miller's mixture, so useful for generating the precursors of complex molecules like proteins and DNA. Thus, carbon dioxide is transformed into methane, nitrogen returns as ammonia, and sulfate belches back as hydrogen sulfide. The heat and gases make their way back to the surface, where they break through as the second type of hydrothermal vent. These differ in virtually every detail from black smokers. Far from being acidic, they tend to be quite strongly alkaline. Their temperature is warm or hot, but well below the superheated fury of black smokers. They are usually found some way away from the mid-ocean ridges, the source of fresh-spreading sea floor. And rather than forming vertical black chimneys with a single orifice through which black smoke billows, they tend to form complex structures riddled with tiny bubbles and compartments which precipitate as the warm alkaline hydrothermal fluids percolate into the cold ocean waters above. I suspect the reason that only a few people have ever heard of this type of vent relates to the off-putting term serpentinization, again from the mineral serpentine. For our purposes, let's simply label them alkaline vents, even if this might sound a bit limp compared with the virility of black smokers. We'll see the full significance of the word alkaline later. Curiously, until recently, alkaline vents were predicted in principle, but only known from a few fossil deposits. The most famous, at Tina in Ireland, is about 350 million years old, and set Mike Russell thinking back in the 1980s. When he examined thin sections of the bubbly rocks from near the fossil vent under an electron microscope, he found the tiny compartments were a similar size to organic cells, 1/10 of a millimeter or less in diameter, and interconnected in labyrinthine networks. He postulated that similar mineral cells could be formed when alkaline vent fluids mingled with acidic ocean waters, and soon succeeded in producing porous, rocky structures in the lab by mixing alkalis with acids. In a Nature letter in 1988, Russell noted that alkaline vent conditions should have made them an ideal hatchery for life. The compartments provided a natural means of concentrating organic molecules, while their walls, composed of iron-sulfur minerals such as makinawite, endowed these mineral cells with the catalytic properties envisaged by Günther Wechtershauser. In a 1994 paper, Russell and his colleagues proposed that life emerged from growing aggregates of iron sulfide bubbles containing alkaline and highly reduced hydrothermal solution. These bubbles were inflated hydrostatically at sulfidic submarine hot springs sited some distance from the oceanic spreading centers 4 billion years ago. The words were visionary, for at the time such a living deep-sea alkaline vent system had never been discovered. Then, at the turn of the millennium, scientists aboard the submersible Atlantis stumbled across exactly this kind of vent around 15 kilometers from the mid-Atlantic ridge on an underwater mountain that also happened to be called the Atlantis Massif. Inevitably named Lost City after the mythic metropolis, its delicate white pillars and fingers of carbonate reaching up into the inky blackness made the name eerily appropriate. The vent field was unlike any other yet discovered. Some of the chimneys were as tall as the black smokers, the largest, dubbed Poseidon, standing 60 meters proud. But far from being stolidly robust structures, these delicate fingers were ornate as Gothic architecture, full of vacuous doodles, in John Julius Norwich's words. Here the hydrothermal exhalations were colourless, giving the impression that the city had been suddenly deserted and preserved for all time in its intricate Gothic splendour. No hellhole of black smokers, these were delicate white non-smokers, their petrified fingers reaching for heaven. Invisible they may be, but the exhalations are real enough and sufficient to support a living city. The chimneys are not composed of iron-sulfur minerals. Hardly any iron dissolves in oxygen-rich oceans. Russell's predictions relate to much earlier times. But their structure is still porous, a maze of microscopic compartments with feathery aragonite walls. Curiously, the old structures that have fallen silent, no longer bubbling with hydrothermal fluids, are far more solid, their pores clogged up with calcite. In contrast, the living vents really are alive, the pores a hive of industrious bacterial activity in which the chemical disequilibrium is exploited to the full. Animals there are too, rivaling the black smokers in diversity, but falling far short in terms of sheer size. The reason appears to be a matter of ecology. The sulfur bacteria thriving in the black smokers readily adapt to life in their animal hosts, while the bacteria, or strictly archaea, found in the lost city don't form such partnerships. Lacking internal farms, the vent animals grow less efficiently. Life in the lost city is built on the reaction of hydrogen with carbon dioxide, which is actually the basis of all life on our planet. In the lost city, unusually, the reaction is direct, while in practically all other cases it is indirect. Raw hydrogen, bubbling from the ground as a gas, is a rare gift on our planet, and life is normally obliged to seek out occult supplies, bound in tight molecular grip to other atoms, as in water or hydrogen sulfide. To rip hydrogen from such molecules and bind it onto carbon dioxide costs energy, energy that comes ultimately from the sun in photosynthesis or from exploiting chemical disequilibria in the vent world. Only in the case of hydrogen gas itself does the reaction take place spontaneously, if painfully slowly. But from a thermodynamic point of view, the reaction is a free lunch that you are paid to eat, in Everett Schock's memorable phrase. In other words, the reaction generates organic molecules directly and at once releases a substantial amount of energy that can, in principle, be used to power other organic reactions. So Russell's alkaline vents fit the bill as a hatchery of life. They are an integral part of a system that turns over the surface of the globe, promoting the restless volcanism of our planet. They are perpetually out of equilibrium with the oceans, bubbling a steady supply of hydrogen that reacts with carbon dioxide to form organic molecules. They form a labyrinth of porous compartments which retain and concentrate any organic molecules formed, making the assembly of polymers, like RNA, far more likely, as we'll see in the next chapter. They are long-lived. The lost city chimneys have now been venting for 40,000 years, 2 orders of magnitude longer than most black smokers. And they were more plentiful on the early Earth, when the cooling mantle interfaced more directly with the oceans. In those days, too, the oceans were loaded with dissolved iron, and the micro-compartments would have had catalytic walls composed of iron-sulfur minerals like the fossil vents at Tina in Ireland. They would have worked, in fact, as natural flow reactors, with thermal and electrochemical gradients circulating reactive fluids through catalytic compartments. That is all very well, but a single reactor, however valuable, scarcely constitutes life. How did life progress from such natural reactors to the complex, marvelous tapestry of invention and ingenuity that we see around us? The answer, of course,